theta, 1 minus cosecant theta. Anything on the right that you want to do at this point?
The top, well, the top would become the same as the bottom.
Just so I'm sorry, on the right one over here, the 1 plus cosecant theta cotangent theta. Do you want to change this to sine or cosine? Do you want to like write 1 over cotangent, cosecant over cotangent, anything like that stand out to you?
Can't you just do the same thing to the top as you did to the denominator?
You generally don't manipulate the like you wouldn't manipulate the 1 plus cosecant theta. What I'm suggesting here is you write 1 over cotangent theta, cosecant theta over cotangent theta, possibly. You know, I'm not sure, but that's one possibility. Do you follow how I did that? Is that okay?
Oh yeah, okay, you just split it.
Yeah, just split it. I don't know. These are just sort of like you're gonna have to deal with it eventually, so you might as well do it in this step here. So let's just see where this goes. So on the top, it's cotangent theta, 1 minus cosecant theta. On the bottom, it's just so much better if you can get it down to 1 minus cosecant squared theta. You know, doing the difference of squares backwards just really saves you some time there. So now, do you see any identities in play on this 1 minus cosecant squared theta?
It would equal cotangent squared.
Close, really close. This one's not, it's not in the perfect form, but you can move the cosecant squared left in the identity, and then you can move the cotangent squared right, so it ends up being negative cotangent squared. Okay. So you know, whether you want to do that or not, that's, you know, it's your call. But it ends up being 1 minus cosecant squared theta equals minus cotangent squared theta. So yeah, so the bottom becomes minus cotangent squared theta. And then minus cotangent squared theta. And then again, you have some options here. Let's just focus on this part right here. Anything you see from this point that you can do?
Cotangent. Can the cotangents cancel?
Yes.
Yeah.
You definitely want to do that. Now this minus, you probably want to move it up to the top. So it'll be minus 1 minus cosecant theta over cotangent theta, like that. And this is where you almost want to go back to you want to always have your eye on like multiple parts of this, but the original was plus 1 plus cosecant theta cotangent theta. And see how the bottoms are the same?
Yeah.
And that's really good. Whether that like I don't know if that was intended, but that's worked out really nicely. So I was going on about, well, maybe you should break them apart. That would have been fine too, but this may, you know, may do something here. So what should we do next? What's your where are you kind of thinking?
Can you distribute the -1?
Yes. So it'd be -1 plus cosecant theta over cotangent theta plus 1 plus cosecant theta all over cotangent theta. You see anything here?
Um, well, their denominators are the same.
Yes, and then you want to combine them now. At some point, because your answer, I mean, your right side is 2 secant theta, like that's your goal. You want to say, well, how can I get to that? Well, I got to combine these things eventually. -1 plus cosecant theta +1 plus cosecant theta. Now what do you see?
You just the ones cancel and then you get 2 cosecant theta.
And that's really good because we finally have that 2. You know, I didn't know where that was going to come from, but now you've got the 2. That's good. Question is, does this become secant theta? And you could just write the answer, but you really should show it. Any idea how to do that?
Um, can you split it into 2? Or
No splitting here. This goes back to one of the very first strategies.
oh, so the bottom would become cosine over sine, and then cosecant would become 2 and then 1 over sine.
Okay, very good. I mean, you're basically there, but you still have to do a couple, you have to do a little bit here, or at least acknowledge something. What happens from here?
So the sines cancel.
They sure do. And, depending on your comfort level, you basically can rewrite this as 2 over cosine theta. And remember, your goal is 2 secant theta. Is this done? Is this done?
No, it isn't.
Double
Well,
check.
2,
Double check, because 1 over cosine is. So this is really
whenever
1 over.
whenever cosine is secant.
That's right. So that's enough.
Oh. Well, it's 2 divided by 1 over cosine though.
No,
So
no, no.
just
It's 2 times because there's 2 over 1. You can write the 2 off to the side. It's not 2
oh
divided by
yeah.
it's a fraction bar there. Okay, so I think we've got it. Probably at least one other path to go to get there. I mean, we could have split everything up into sine and cosine to start, but I think you went down the path I would have gone down. So really good. Where should we go from here? Which problem?
What do you think's the most like complicated one? Because he said that those are the ones that are gonna be on the test.
I mean, they basically get more complicated as you go. I mean, these are all more difficult than the average one. So, I mean, like, I know I think we've done 80. We've probably done all these, but I couldn't say for sure.
I don't think we did 80 yet.
Okay. You want us to work on 80 then?
Yeah.
Okay. Okay. And that could always be a misdirection by your instructor, oh no, the really difficult ones, then they're not the difficult ones. They're just trying to motivate you to study. Okay. There's a lot here, meaning like both sides are fairly complicated. So this might be a both. Might be that you work one side and then you have to work the other for a little while. Does anything stand out to you when you look at these?
On the right side, can't you just split it?
You
into two
cannot,
fractions.
you can't split it when it's on the bottom like that. Only when it's a single, like here's what you just asked me. X over X plus Y. This cannot be split. But if it were X plus Y over X, this one you can split into X over X and Y over X.
Oh,
So it's only when there's a single thing on the bottom, single term.
well, these are all like 1 over cosine, 1 over sine. So can't the 1 over cosine become secant squared?
Yes, yes. I mean, so you can work on the left. So secant squared t plus cosecant squared t, okay? And I mean, there's no identity for that. So that you're like at sort of a standstill. Because you really, if you notice, the thing on the right is a single fraction. There's two fractions on the left.
Yeah.
So this almost takes you away from your answer because you still have to combine them into one, or you have to somehow split up the right-hand side, which I already mentioned you really can't here. So do you see anything else?
Well, it's sine plus cosine, except 1 over cosine and 1 over sine, but it's one of the Pythagorean theory or Pythag identities.
Not in this form though. It's got to be exactly sine squared plus cosine squared, not on the bottom. Like they can't be split up by plus. So here's some suggestions. Okay, I'll give you two suggestions here. One is to make a common denominator on the left. Okay. The second is to factor out a cosine squared t from the bottom on the right. You may have to do both. You may have to do both of these, but you at least need to do one of them to get kind of going. Do either of those mesh with you or make you say, oh, yeah, kind of that makes sense to me. I should do that one.
You have to make both of them sine.
Which one?
So like it says common denominator on the left.
Yeah. So again, like always think of it like it's 1 over x squared plus 1 over y squared. How would you make a common denominator for x squared and y squared?
Combining them.
Yes, you can always just multiply them. Okay, so let's do that here. So I'm going to write this out. 1 over cosine squared t, and then you multiply the top and bottom by sine squared t, plus 1 over sine squared t, cosine squared t, cosine squared t. So I assume this is what you meant, right? By multiplying them?
Yeah.
Okay, so the numerator you can combine because they have the same denominators. And now you should see something.
Yeah, let me write this down.
Yep.
So wouldn't it become, so it'd be sine over cosine plus cosine over sine?
You don't want to split these apart. Like you've gone to the trouble of making a common denominator. You don't want to split it apart. Maybe I misunderstood, but like, and you don't cancel these either. Like if you cancel them, you just go back to where you started.
Yeah.
So is it clear how I wrote this line, or is it not clear? Because
No,
okay.
it's clear. I just don't really know where to go from there.
Well, you mentioned it earlier. Sine squared plus cosine squared is an identity.
Yeah.
Okay,
Oh,
so
it's 1.
right now, why is that important? Is because when you look at the right side, you're kind of getting closer because the right side has a, let's snip that in here,
1 on the
1 on the top.
numerator.
Yeah, so it's like, all right, well, that's pretty good. So again, like you could keep working on the left, or you could start working on the right. Both will get you there.
How about we try the right side?
Okay. So what would you try on the right side? What is sort of standing out?
Um, cosine squared t minus cosine the 4th power of t. So for this one, you also wouldn't split it because you want to keep the 1 on the top, right?
That's
Or
right.
can you split it?
We just talked about up here. Like you can only split it when it's a single term on the bottom,
Yeah.
and there's 2 terms. You can't split it. But you should really be like the intent here is that you notice there's a squared and a 4th, and something factors out of both of them.
The 2 factor out?
Cosine squared. Cosine squared can be factored out of both of them. So the analogous problem is it's x squared minus x to the 4th on the bottom, and you can factor out an x squared from both.
Oh, yeah, I kind of figured that's what it was, but I forgot you could do
Yeah.
that.
So what goes in parentheses here?
Negative cosine squared t.
Anything
Or no,
else?
wait.
Because when you multiply in, you have to get back to the previous line.
Oh, 1.
Okay. Now we're in good shape here because cosine squared t, cosine squared t. So reasonably, it should follow that 1 minus cosine squared t is sine squared t.
Enter t.
And that's the first Pythagorean identity. So if you subtract cosine squared t from both sides of the equation, or theta, sine squared theta equals 1 minus cosine squared theta. So you can replace 1 minus cosine squared theta with sine squared theta.
So it becomes 1 over cosine squared plus sine squared theta.
T, but yeah.
Oh, t. Well, yeah, and
Yeah.
that's the same as the left side.
Yes. Now we've got it. So again, you could have worked this one right here on the left using the same identity, because the sine squared t could have become 1 minus cosine squared t.
Yeah, I just figured the right side would be easier.
Yes, you
It's
can.
easier to reduce down than to make it go up.
Yep, I agree. So when you hit a wall on one side, you go work on the other. Okay, so that is 80. Which one do you want to do next?
About 79.
Sure. Okay, so here's 79. Which I think there is a side that's more complicated. Which one would you express as being more complicated?
Probably the right side.
Yeah, I agree. And even though this 1 minus tangent x1 plus tangent x, we know what to do there, it's more about which one is more complicated. So whenever you see squareds, you really should think identities. So is there an identity that comes to mind for secant squared?
So tangent squared plus 1.
That's right. Okay, so I think it's reasonable, especially since the answer has tangent in it, to use that identity like from the start. So this becomes tangent squared x plus 1 plus 2 tangent x over 2 minus parentheses. Why am I using parentheses here?
Um,
It's because we're replacing secant squared x, and it's two terms that do that. So you have to remember to subtract both of them.
Oh, okay.
If you don't, you will miss the answer by a long ways. You'll just never get there. And it's something that tiny that could be the difference between, taking a few minutes to do it and 30 minutes, banging your head against the desk, frustration. Okay, so now that we've used that, what say you? What should we do from here?
Two tangent x. I feel like both the tangent squared x's do something.
So you can't. You have to really look at this like there's impenetrable brick walls, top and bottom. Like you can't do anything with the top and the bottom quite yet. Like just look at them individually. And I would suggest looking at the bottom first. There's something kind of straightforward you can do on the bottom that's doesn't give you the answer, but it,
Distribute the -1.
yes. So that becomes 2 minus tangent squared x minus 1. And then what does that become?
Tangent. Yeah, let me just write this down.
Sure. Sorry, I get very excited and then I expect you to just blurt out the answer.
Oh, it's 1 minus tangent squared x.
Yes, so your bottom is 1 minus tangent squared x. Now let's focus on the top. Okay. I'm gonna rewrite it here and see if that helps.
Tangent squared x plus 2 tangent x plus 1.
So here's another strategy is to rewrite it without the trig functions. That's the top. Does that look at all familiar to you?
It does, as a matter of fact.
Okay. How would you factor that?
Well, this is a while ago. I have to remember that. So can't you just factor out the U?
No, that would be if they all had a U in them. These do not have a U in them.
Oh,
It's the type of
I know what
factoring.
it is. I can't remember it.
Okay, so two numbers that multiply to 1 but add up to 2.
Yeah, that's what it is. So it'd be U.
So two numbers that multiply to 1 but add up to 2.
So it'd be U plus 1 and then U plus 1.
Yes. Okay. In fact, it's a perfect square trinomial, so you end up writing U plus 1 squared.
Yeah.
Okay. Now, what is U in this problem? Like, what was I really claiming U is over here on the right?
Tangent.
Yes. So that means it becomes tangent x plus 1 squared like this. Or if you don't like that, it's tangent x plus 1, tangent x plus 1. Like these are both equivalent. Is that okay?
Yeah.
Okay. The bottom is a different type of factoring. I'll do that in a different color here. It's 1 minus x squared. Do you remember this type of factoring? Two terms.
1 minus x squared. So don't they have to cancel each other out so it equals 0?
No, this is a difference of squares. Difference of squares. So it's a squared minus b squared. And this becomes a minus b, a plus b. So your a is whatever you square to get back to 1, which is 1. B is whatever you square to get x squared. So minus x, 1 plus x.
In the case of this problem, it's tangent.
Yes, so it's tangent on, so the bottom becomes what? What goes on the bottom?
Um, 1 minus tangent x times 1 plus tangent x.
Yes, 1 minus tangent x, 1 plus tangent x. Okay, now everything's in parentheses, so you can make cancellations.
So both the tangent x plus 1 and then 1 plus tangent x would cancel.
That's right. Now it's been so long since we looked at the original. Is that what we wanted? Is that, is this actually the answer?
It is actually.
Yeah, it is. So we should have been keeping an eye on that a little bit closer, but it ended up working out. So a question you might ask your teacher to sort of like figure out, well, is this going to be on the test? You might say, well, we have to know any factoring. And if the answer is yeah, you need to know difference of squares and perfect square trinomials, then you know that you're probably going to use this. This one's probably on there.
My teacher has like a system where he calls these like level 1 through 5. So like
Okay.
75 through 80, he calls their level 5 problems because they're the
Yeah.
most hard.
Yes.
And his
I'd
level
agree.
4s and his level 3s. So he said that the test is going to be all level 4s and all level 5s.
Okay. So I would think he's breaking it up like 3 and 2 or something like that, or 2 and 1. I think you
So
mentioned.
most likely he's going to give us a question on this, or he's going to give us 3 questions on this worksheet here.
Yes. Okay.
So I'm just not sure if like he's going to tell us what they are before. Or
Well, you can just keep asking, you know,
yeah,
begging. I mean, whatever, you know,
I
whatever
don't
you
even know
think.
when the test is.
Right.
Yeah, I could definitely do that.
Okay, where should we go from here? Got, time to do maybe all of them, not sure, but
Um, so we did 76 and 78. So we did 77.
we've not today. I couldn't say for the past.
Yeah,
Um,
so we can just do 77 because we haven't did it before.
okay, sounds good. All right, so just this is the initial observation I want you to have when you look at a problem like this one is they're kind of both equally complex. Yeah, they both have something on the top, a 1 plus something on the bottom, which means it's probably a both, meaning both sides. Besides that, does anything stand out to you now that you've looked at it for a moment here?
Um, so would it be smart to make everything into sine and cosine?
So we talked about that in the previous one, and I think it will work. It doesn't get you there. It's not that doesn't like that isn't the only thing that you'll have to do, but it does get you there, get you closer. So we can certainly do that. All right, so let's try that. So secant is 1 over cosine x, and tangent is 1 plus sine x over cosine x. Do you want to do the right side as well, or just the left?
The right side too.
Okay, 1 over sine x, 1 plus cosine x over sine x. So you've made it worse, but it will get better. Yeah, but depending on what you do here.
So on the left side, the cosines cancel.
They do not. They do not. It's got to
Oh
be.
yeah, so yeah. So one of the cosine. How come the cosines can't cancel?
There's parentheses in the denominator. So the whole thing would have to cancel,
Oh,
meaning you'd have to have a 1 plus cosine or 1 plus sine over cosine in the bottom here.
yeah, I'm stuck.
Well, so you had some idea going down this road. I mean, you had some hope, right? What was your hope?
Uh, it would just factor out nicely.
These are level 5s though. These are not.
Yeah.
Okay, but like just look at the one on the bottom here. And like again, the analogous problem is like 1 plus x over y. Like what would you do to simplify that?
1 plus x over y.
So I think I made that list for you last time. I think you also need sort of like for lack of a better word, an algebra list of things you're looking for. So we've talked about conjugate, common denominator. That's the one that applies here. Factoring, foiling. Okay, these are all things that you need to go down your checklist. Are you allowed a note card on this?
No.
Okay. So you need to memorize or sort of look for that. Like when I see this, I'm like, oh, we can make a common denominator because the answer doesn't have a 1 in it, especially if we're manipulating both sides. And I know that might lead to canceling the cosines. So what would the common denominator be in this bottom one?
Um, do you multiply everything by cosine?
The top and bottom on the left, yeah. So it ends up being times cosine x times cosine x. So let me rewrite this here. So it's 1 over cosine x over cosine x over cosine x plus sine x over cosine x. And I don't want to be too distracting, but we really should probably do the same thing on the right here. But we can do that later or do it in this step. What would you like?
Can we just focus on the left side?
Sure. So the whole reason of doing that is you really want to make a common denominator. Do you have a common denominator down here, just in the bottom?
Yeah, you do.
Yeah, so this becomes 1 over cosine x over cosine x sine x over cosine x. And now you can cancel something. Sorry, there's a plus there, plus. Now you can cancel something.
The cosine.
Yes. And the reason is like, yeah, there's parentheses, but it's the only thing in parentheses. So this becomes 1 over cosine x plus sine x. So this is a step where you're really in a bad spot because the right hand side doesn't look anything like this. Like if you go
No.
back to the original problem, like you're not even close. So you at some point knew you were going to have to work on the right side. Now is probably the time to do that. Again, I don't know. Yeah, I think we talked about like puzzles. It's like, well, I've done as far as I can on this part of it. So let me go work on something else. Is that okay? Can we go back and work on the right hand side?
Yeah.
Okay.
Yeah.
So really no reason not to do the same thing that we did on the right side as we did on the left. Make a common denominator. What is that common denominator?
Sine.
Sine x is sine x, sine x. So here we go. It's 1 over sine x over sine x over sine x plus cosine x over sine x. Okay. Why don't you try it from here and see if you can get the final answer. It's really just going to fall out of you doing a little bit of work on the right hand side, similar to what we did on the left.
I got it. It's pretty much the exact same thing on the left.
Yeah.
The sines cancel, then becomes
Yes.
1 over sine x plus cosine x, which is the same.
Yes. So if there's anything that you're learning here that could apply to things in the future is like, if you do every problem that could be on the exam and you know how to do every problem that could be on the exam, you should know how to get every problem right on the exam. It's like the brute force method of studying. Like, you know, if you had infinite time and infinite resources and you could learn every problem, you could always ensure that you would get a 100% on the exam. That's kind of what you're seeing here with this. Again, it's unlikely, but that you would have that much time to do this, but it is a strategy. It's how the first sort of people that broke codes did it. They had enough time. They tried every possible combination, and there still are computers that try to do that now.
What's probably gonna happen is he's gonna give us the questions before the test. He'd be like, oh, okay, this is a test. You have to memorize these and then write them down, because that's what he did on the last quiz.
Good. Yeah. Hopefully that's the case. Yeah. Schedule a lesson and we'll work through them.
Mm-hmm.
Okay, we got some time here. 76, 78, or go to another grouping of questions.
Can you make another problem that's similar to the last one we did?
77.
Yeah.
So the problem is I don't know if it will work. I guess I can check. Yeah, let me check real quick. These can be checked by graphing. So let me see if I can get okay. So we got cosine x over 1 plus cotangent x. And then equals sine x over 1 plus tangent x. It's the best I can come up with. These are hard to make up. But if you want to try this one, you can.
Okay.
It's not exactly the same, but it does work out. Like like I said, it's hard to make them exactly one for one. Some of the earlier ones you can, but these get out of hand.
So this would probably be a both side, right?
Oh yes, it is. How are you? How are you doing on this one? Or getting short on time?
The left side is making me a little stuck.
So it's 1 plus cosine x over sine x. and then you make a common denominator, so it's cosine x over, and ends up being sine x plus cosine x
Yeah,
over
that's what I
sine
just
x.
found.
And what's different about this one is you don't cancel. The sine x just goes up into the top. So it ends up being cosine x sine x over sine x plus cosine x.
Yeah, I got the right side.
And then the right
So,
side is going to do the same thing. It's going to be, it's a, it's a mirror image, sine x over cosine x, sine x over cosine x plus sine x over cosine x, because you make a common denominator. And then that cosine goes to the top. They go to the top there. So it becomes sine x cosine x over cosine x plus sine x. You can see that it
yep.
does in fact, work here. So the so I guess we got a lesson tomorrow. I mean, I'm happy to do more of these. If you have time, I mean, try some on your own, see if you make any headway there. But it's a lot of ways like programming. A lot of programmers just figure it out on their own. There's not really like a path. But just give that a try, see what you come up with, and we'll try it. We'll do some more tomorrow. But
Yeah, the only problem is I don't know the questions we do tomorrow